Hello everyone. Today I will present our paper LowFormer Hardware Efficient Design for Convolutional Transformer Backbones. We present a new vision backbone architecture family, namely LowFormer. The architecture design is fueled by insights we gained through testing common design decisions and analyzing the hardware efficiency. It is a joint work of me, Moritz Nottebaum, Matteo Dunnhofer and Micheloni. We are all associated with the University of Udine and are part of the Machine Learning and Perception Lab. Vision backbones are a vital component in many computer vision applications. If the efficiency of backbones is increased, the efficiency of downstream tasks is also automatically increased. For this reason, many applications try to optimize the architecture of vision backbones and optimize their speed-accuracy trade-off. But how do we measure efficiency? A common metric is counting mags. The mags of a model refer to the amount of mathematical operations a model needs to finish its execution. However, mags are not a reliable predictor of execution time. We will now confirm this with experimental data. We will specifically look at different design decisions and how they influence the relationship between mags and actual execution time. Here we compare depth-wise convolutions and standard convolutions, namely ungrouped convolutions. Depth-wise convolutions do not combine the input feature maps and process each feature map separately. On the left we can see a model with standard convolutions and a model with depth-wise convolutions. We compare their mags and GPU latency. Both have a similar GPU latency, but the standard convolution features 4 times as many mags. We can see that depth-wise convolutions execute mags far more inefficiently. On the right side, we repeated this experiment with a different model configuration. The imbalance between mags and execution time persists. Now we will take a look at how operating resolution of model layers affects execution time relative to the mag amount. We compare two models again. One operates on a lower resolution than the other. The lower resolution model has a higher channel dimension, such that both models have a similar amount of mags. We will depict the relative GPU latency of the models to each other. On the left we can see that the low-resolution model with high channel dimension is much faster in terms of GPU latency. That is nearly 3 times as fast. The same also applies to the models on the right side. Here the difference is smaller, however. The lower resolution model is only twice as fast. As a reminder, the figures depict the relative GPU latency of the models to each other, not absolute numbers. At last, we will take a look at the mobile inverted bottleneck block, abbreviated as MBConv. The original version features a pointwise convolution, followed by a depthwise convolution, and then finished by a pointwise convolution again. The pointwise convolutions increase and decrease the channel dimension by an expansion factor. In this figure, it is 4. The fused MBConv block now fuses the pointwise convolution and the depthwise convolution into a standard convolution. As a result, the fused MBConv block consists of a standard convolution and a pointwise convolution. The fused MBConv usually has a far higher amount of mags than the unfused one. However, as we remember, depthwise convolutions do not execute their mags very efficiently. Therefore, we analyze either efficiency experimentally. Here we plot the average execution time of the fused MBConv divided by the original MBConv. The x-axis refer to different input resolutions. 2 lines represent channel dimension 128, which is the blue line, and 256, the orange line. The execution time is again the relative execution time of both layers. Therefore, if a line is over 1, the original MBConv is faster for the configuration of resolution and channel dimension. If the line is under 1, the fused MBConv is faster. We can see that for many configurations, the fused MBConv is faster than the original one. This is especially true for channel dimension of 128, the blue line. Regarding efficient execution of mags, the fused MBConv has at least 4 times as many mags, even though it is faster or similar fast. Let us now look at channel dimension 512. For high channel dimensions, the fused MBConv becomes increasingly inefficient. Its relative execution time approaches the relative amount of max, compared with the original MBConv. We have shown experimental results that support the statement that max are not reliable predictor of execution time, but we have also learned something. Operating on a lower resolution is faster than operating on a higher resolution, and max failed to predict the actual execution time reliably. And the fused MBConv is faster than the original MBConv in many scenarios. We use these insights to design a hardware-efficient vision backbone architecture. We name it LowFormer, as from Low Resolution Transformer. Let's take a look at LowFormer's architecture design. We start with the macro design. We use a very simple, repetitive design with 5 stages. Each stage begins by reducing the resolution by 2, as it is common with backbone architectures. In the first 3 stages, we rely purely on convolutions. We start with a normal convolution and continue with MBConvs. In the last 2 stages, after the downsampling of the feature maps, follows a LowFormer attention block, which we will discuss later. It is then followed by an MBConv block. The LowFormer attention block and the MBConv block is repeated n times, depending on the version of LowFormer. Our hardware-efficient macro design follows 2 principles. To let a model operate on lower resolution is, in many cases, more efficient than operating on a higher resolution. The fused MBConv is faster than the original MBConv in many cases. We therefore employ few layers in the high-resolution stages and apply the fused MBConv for low channel stages, while for high channel stages we apply the original MBConv. If we compare LowFormer with the same model, but it only employs the original MBConv, we see that accuracy and GPU throughput drop significantly, while latency remains similar. The fused MBConv can have a positive effect on efficiency and accuracy. Let's come to our micro design. We present LowFormer attention, which is a very simple adaptation of the original multi-head self-attention. We only add 2 convolutions around the original multi-head attention. However, these convolutions downsample the feature maps by a factor of 2. The linear projection layers also reduce the channel dimension by 2. If we remove the downsampling, the accuracy does not increase, but latency and throughput worsen considerably. If we now exchange the LowFormer attention, for example with the recently published attention adaptation named ReLU linear attention, we can see that LowFormer attention yields better accuracy results and higher efficiency. LowFormer variants achieve state-of-the-art results in terms of speed-accuracy trade-off. In this figure, we will compare LowFormer with the most recent backbone architectures. The more model is to the top right, the better its speed-accuracy trade-off is. LowFormer variants are blue. LowFormer is able to outperform all recent architectures by a clear margin in terms of speed-accuracy trade-off, regarding, for example, GPU throughput. When employing LowFormer as backbone in an object detection model, it achieves high efficiency paired with high accuracy. The same holds true when LowFormer is implemented in a semantic segmentation model. In summary, max are not a reliable predictor of execution time. This is especially true when depthwise convolutions are employed and when a model operates on a high resolution. Because of its hardware-efficient design, LowFormer achieves state-of-the-art ImageNet classification results, trumping many recent approaches in terms of speed-accuracy trade-off. The results also show that the downstream tasks object detection and semantic segmentation can profit from LowFormer's efficiency. Thank you for listening. For more information and exact evaluation results and numbers, please refer to our paper.